In this mini lecture, I'm going to look at something called the binomial theorem. Now, in other algebra classes, we've learned how to do stuff like, take a plus b quantity squared. Right? So we do FOIL on that. It's really a plus b times a plus b. And when I do FOIL, a times a is this a squared, a times b and b times a give me these two middle terms, and then last b times b is the b squared. So we get a squared plus 2ab plus b squared. Now, we're going to look at higher powers of this in this lecture today. So how I'm going to start is if I want a plus b to the third power, that's really just a plus b times a plus b squared, right? There have to be three total a plus b's. But I already know what a plus b squared is. We just figured that out. That's a squared plus 2ab plus b squared. So I need to multiply everything by a first. So a times a squared is a cubed. Right? I'm just doing that. Then I'm going to get a times 2ab and a times b squared. So a times 2ab will be 2a squared b. A times b squared will be ab squared. Then I'm going to multiply this plus b times everything. So that's going to get distributed to these three parts. So I'm going to get plus b times a squared. So that's a squared b. And then plus b times 2ab. So that's 2ab squared. And then b times b squared is b cubed. And now I just look for like terms. There's only the one a cubed. As far as a squared b's are concerned, I've got some a squared b here and an a squared b here. So 2 plus 1, I get 3a squared b. Same thing happens with the ab squareds. I have 1ab squared and then 2ab squared. So that's 3ab squareds. And then just one lonely b cubed at the end. Now, I'm just going to do one more expansion, and then we're going to look for a pattern and see if we could figure this out any other way. So a plus b to the fourth would, again, I'll just peel away one of those a plus b's, and then there'd have to be 3 left over, right? We have to have a total of 4. But I already know what that second one is. I just did that, right? A plus b to the third is a to the third plus 3a squared b plus 3ab squared plus b to the third. And I'm going to do the same sort of thing. I'm going to multiply a times all 4 of these terms. All right, so a times a to the third is a to the fourth. A times 3a squared b is 3a cubed b. A times 3ab squared will be 3a squared b squared. And a times b cubed will just be a b cubed. Okay, now I'm going to multiply this plus b times everything. And I'm going to write it below just because I'm running out of room. So b times a cubed will be an a cubed b. B times 3a squared b will be 3a squared b squared. B times 3ab squared will be 3ab cubed. And b times b to the third will be b to the fourth. So I'm just distributing there. And now I combine. I get a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. Now, there are some patterns we can sort of notice from this here. So on this next page, I've just listed what we've done here. So here's a plus b squared. Here's what we found for a plus b cubed. Here's what we found for a plus b to the fourth. So we can describe what would happen if I do a plus b to the nth. So what's the first term? Well, here my first term was just a squared. Here it was a cubed. Here it was a to the fourth. It's just the same as what this exponent is. So if I have a plus b to the nth, I would expect that the first term is going to be a to the n. And what happens to the exponents on a as I go across? Here I have a to the second, a to the first, and then no a. A to the third, a to the second, a to the first, no a. A to the fourth, a to the third, a to the second, a to the first, and no a. So the exponents on a decrease by 1 in each term. So the exponent on a in the last term is really 0 because a to the 0 is 1. So I could really say that what I have here is that in each of these cases I could throw on a little a to the 0. That wouldn't change anything. So then I've got a to the fourth, a to the third, a to the second, a to the first, a to the 0. Get rid of those though, it sort of makes it a little messy there. Now what about the exponents on b? Well, no b, b to the first, b to the second, no b, b to the first, b to the second, b to the third, b to the fourth. So they increase by 1. In each term. So what about the first term? There's no b, but that's really then b to the 0 at the beginning. And the last term in each, well, b squared, a plus b squared. B cubed, a plus b cubed. B fourth, a plus b to the fourth. If it was a plus b to the n, then the last term is going to be b to the n. What about the sum of the exponents on the variables? Notice here, if I look at this, that's just a 4. If I look at this, 3 plus 1 is 4. If I look at this, 2 plus 2 is 4. If I look at this, 1 plus 3 is 4. And if I look at this, of course, that's just 4. So the sum of the exponents on the variables in each term always equals n, which is the power on the original binomial. And how many terms are there? Well, I had 3 terms, 4 terms, 5 terms, but that was second power, third power, fourth power. So there's always one more term in the expansion than in the original, than the power on the original. So if it's the nth power, there's going to be n plus 1 terms in the expansion. So I can sort of predict what the expansion is going to look like without actually doing it. So that's here example 1. Write the variable parts of the terms in the expansion of a plus b to the 6th. And I said, for now, let's not worry about the coefficients. So what we've got here is n is equal to 6. So I always start with whatever a is to that power. So I'm going to start with just a to the 6th. And as I go through, I don't know what that coefficient is. As I go through, well, I do know it's a to the 6th. We figured that out. But I don't know what the next coefficients are going to be. I don't know what this is going to be. But my a has to go down 1, a to the 5th. And my b has to come up 1, plus those exponents have to add together to equal 6. So what's next? Well, a would go down 1, b would come up 1. 4 plus 2 is 6. What's next? A would go down 1, b would come up 1, 3 plus 3 is 6, and so on. So those would be the variables, at least, if I multiplied out a plus b to the 6th power. I don't know what the coefficients are, but I know what the variables look like. Now, to find the coefficients, there's 2 ways we can do this. A mathematician, Blaise Pascal, discovered a triangular pattern that can lead to the coefficients that we've looked at here. The way this pattern works, it always starts with a 1 on the top. And then when I go down to the next row, I always move to the left a little and right a little. And the far left is always 1, the far right is always 1. So the next row I do the same thing. I move a little bit to the left and a little bit to the right, and those are 1s. This value in the middle, where it comes from, is I take the two values above it and I add them together. So 1 plus 1 is 2. And then here I put another little 1 and another little 1, but now I'm going to have two numbers in between. So I'm going to take this 1 and this 2 here, and this 2 and this 1 here, and add them together. So 1 plus 2 is 3, 2 plus 1 is 3. Next row, I put a little 1, I put a little 1. I'm going to add these two, I'm going to add these two, I'm going to add these two. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. Notice those numbers, 1, 4, 6, 4, 1. Right? 1, 4, 6, 4, 1. Look up here. 1, 4, 6, 4, 1. Right? If I have this a plus b to the fourth here at the top, the coefficients going across are 1, 4, 6, 4, 1. If I wanted to figure out my coefficients up here, we know that this is a plus b to the fourth. This is actually a plus b to the third. This is a plus b to the second. This would be a plus b to the first, right? Because that's just 1a plus 1b. And this is really a plus b to the 0. Anything to the 0 power is 1. Right? So I've got a plus b to the 0 is 1. A plus b to the first is just a plus b. A plus b squared was a squared plus 2ab plus b squared. A plus b cubed, I had those numbers 1, 3, 3, 1. So this is exactly figuring out what I would have. So how do I do the next row? I don't have to do all these arrows. I can just sort of think through it. I start with the 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And I have a 1. That would be a plus b to the fifth. And now to get the sixth power, I just do one more row. So I bring down a 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 15, 6, and 1. So this would be a to the sixth plus 6, a to the fifth b, plus 15, a to the fourth b squared, plus 20, a cubed b cubed, plus 15, a squared b to the fourth, plus 6a b to the fifth, and then plus b to the sixth. So that would give me one way of finding those coefficients. That's fine if we have a relatively small number for n. If we get much bigger, making that triangle is a little bit time consuming. So there's another way. We have these things called binomial coefficients. So if n and r are whole numbers, my n has to be bigger than or equal to r. Then this expression here, if I have n over r, no fraction bar, but like parentheses sort of around them, I read that as n choose r. It's really sort of the number of combinations of n objects taken r at a time. So I've got so many books in a box and I pull out some of them to read. How many ways can I do that? That's what this calculates. It's calculated with this formula. It's based on factorial. So the n factorial always just stays up here in the top. The r, I get an r factorial in the bottom, and then I get this extra little n minus r factorial in the bottom. We'll see how that works when we do this. What ends up happening, if I multiply these two numbers in the bottom together, they always add up to the top. Sort of like the exponents did earlier. So let's do these here with the formula. So my top is n, my bottom is r. So this is going to be 4 factorial in the top, right? That's n factorial in the top, and then r factorial in the bottom, and then n minus r, 4 minus 0 factorial in the bottom. So this is going to be 4 factorial over 0 factorial times 4 factorial. Now, this is a little bit where I said, you know, why we talked before about how 0 factorial is equal to 1. That's really for this whole thing to make sense. Now, we could figure out what 4 factorial is. 4 times 3 times 2 times 1 is 24. Of course, 0 factorial we've said is 1. And this whole thing then is just going to be equal to 1 overall. What that's really saying is if you have 4 books in a box and you pick 0 of them to read, how many ways can you do that? Well, there's just one way to do it. You just don't pick any books. What about this 4 choose 1? Well, that's going to be 4 factorial in the top, and then 1 factorial in the bottom, and then we'll take 4 minus 1 factorial in the bottom. So that's going to be 4 factorial, 1 factorial, and 3 factorial. Well, there's some nice things here. We've done some work with these factorials before. A lot of stuff ends up canceling out a lot of the time when we have fractions like this, right? So this whole thing is 4 over 1, which is just 4. Now that essentially says, okay, there are 4 books in a box. You're going to pick one of them to read. How many ways can you do that? Well, if you pick one out of the 4 books, there's 4 ways that can happen. So this next one then, we have 4 factorial. We get 2 factorial in the bottom, and then 4 minus 2 factorial in the bottom. So that's 4 factorial, and then I get 2 factorial times 2 factorial. So that's 4 times 3 times 2 times 1, and I get 2 times 1 times 2 times 1. But a lot of that stuff cancels out. I get 12 over 2, which is 6. Now this would say, okay, there's 4 books in a box. You're going to pick a pair of them to read. How many ways can you do that? There's 6 different pairs that you can pick. In a sense, you can pick 4 books first, 3 books second. That gives you 12 possibilities. But this doesn't count the order as important. So that counts book A and then book B is different from book B and then book A. This is just saying how many groups of 2 can you pick. That's why I divide by an extra 2 there. All right, let's finish these up. They're not too bad. We get 4 factorial, and then we get 3 factorial, and 4 minus 3 factorial. That's 4 factorial over 3 factorial times 1 factorial. But I sort of say, wait a minute. Isn't that the same thing? Right? Those two are the same thing. That's just going to give me another 4. Does that make sense with our books? Yeah, it does. This says you have 4 books, you're going to choose 1 to read. Well, when you choose 1 to read, you're choosing 3 not to read. So choosing 1 out of 4 is really the same process as choosing 3 out of 4. We get the same number of ways for that to happen. We always have that kind of symmetry when we do this. Same sort of thing here. We get 4 factorial over 4 factorial times 0 factorial. Well, 0 factorial is equal to 1, and anything over itself is equal to 1. Now, look at these numbers. Are they familiar? 1, 4, 6, 4, 1. Those are exactly the same numbers we had back on this Pascal's triangle, right? As we go across this row, 1, 4, 6, 4, 1. So these binomial coefficients are exactly the values that we have in Pascal's triangle, which are the values we want for my binomial expansion. So that's what I've sort of said here. This is how the binomial theorem then works. If we have a plus b to the n, we always start with n sub 0, and we've got a to the n, and we have b sub 0. Then we go to n choose 1. The a goes down 1, the b comes up 1. And then n choose 2, the a goes down another one, so a total of 2. And now we have b squared. And that continues all the way along. Notice that what's changing here then is the bottom number is going from 0 to n, so I can call that r. R is going from 0 to n. I have n choose r. And then the b always has the same exponent as the number in the bottom. So if it's r in the bottom, it's b to the r. And the a is always here, n minus 0, n minus 1, n minus 2, n minus 3. I just have the top minus the bottom, n minus r. So the exponent on b is always the same value as r. Also, remember the sum of the exponents will always equal n. So how do I do a plus b to the 5th power? Well, what I'm going to need to do 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. So 5 choose 0 will be 5 factorial over 0 factorial, and 5 minus 0 factorial. So that's 5 factorial over 1 times 5 factorial. That's just going to be 1. When I do 5 choose 1, that's going to be 5 factorial over 1 factorial. And, okay, it's going to be 5 minus 1, that's going to be 4 factorial. These bottom two numbers always add up to the top. So that's going to be 5 times 4 times 3 times 2 times 1 over 1 times 4 times 3 times 2 times 1. But most of that cancels out. So I'm left with 5. If I do 5 choose 2, no line. That's going to be 5 factorial over 2 factorial and then 3 factorial. 5 times 4 times 3 times 2 times 1. We get 2 times 1 and then 3 times 2 times 1. So we get 20 over 2, which is 10. And now, what's interesting here, eventually this is always going to happen. Eventually we're going to get something that we've already done before, right? Those are really the same. So, not that. And when I do then 5 choose 4 or 5 choose 5, I'm going to get this symmetry. We came up 1, 5, 10. I just got 10 again. These others have to be 5 and 1. You can do the calculation, but that's what we would get here. So how do I expand this? Well, I just use these coefficients with the way the variables work. So I'm going to get 1, and we start a to the 5th. And then I would get 5. I let a go down 1, b come up 1. And then 10, a goes down 1, b comes up 1. And then 10, a comes up down 1, b comes up 1. And then 5, again down and up. And finally 1, b to the 5th. So we could figure that out without multiplying everything out. I talk a little bit about the symmetry here on the bottom. That usually will help you eliminate some of the work that you have to do. What if I have something like x plus 2 to the 7th? Well, I still just think of it as a plus b to the 7th at the beginning. And so I'm going to need to know what 7 choose 0 is. That's just going to be 1. I need to know what 7 choose 1 is. But after a while you realize, well, wait a minute, if I write this out, 7 times 6 times 5 times 4 times 3 times 2 times 1, and then the bottom I'm going to have 6 times 5 times 4 times 3 times 2 times 1. A bunch of that stuff's just the same, right? All of that's going to cancel. I'm just going to be left with 7 in the top and 1 in the bottom, so that's going to be 7. So then I'm going to need, okay, well, what's 7 choose 2? So that'll be 7 factorial. I always just get the 2 factorial, and then 2 plus what is 7? It has to be 5 factorial. So 7 times 6 times 5. Okay, I've got a 5 factorial in the bottom. Right, but that stuff's all going to be the same. So I'm just going to get 42 in the top and 2 in the bottom, so that's going to be 21. So now what about 7 choose 3? So that'll be 7 factorial, 3 factorial, and 4 factorial. So I always look then, what's the biggest factorial in the bottom? 4 factorial. So that's going to cancel out a lot of the top. So I write the top until I get that. So 7 times 6 times 5 times 4. Now this is 4 factorial on the way down. So I'm going to get 3 times 2 times 1, but then 4 on down. Right? And that stuff cancels. So I'm going to be left with 7 times 6 times 5. That's going to be 210 over 6, which is just 35. When I do 7 choose 4, and you should keep in mind, eventually I'm going to start getting repeats here, and this is where it happens, right? That's the same as that. So that's also 35, and I've started repeating. So if I had just a plus b to the 7th, I start out with 1, and then 7, and then 21. So it's just going to be a to the 7th, 7, a to the 6th b. It was, let's see, what was it again? 1, and then 7, and then 21. A to the 5th, b squared. And then next was 35, a to the 4th, b to the 3rd. But now I start repeating, right? My next one is 35 again. So that's going to be a to the 3rd, b to the 4th, and then 21, a squared, b to the 5th, and then 7, a, b to the 6th, and then finally b to the 7th. But what I want to do here now, I want to let a equal x, and I want to let b equal 2. Because that's really what I had up here, right, was x plus 2 to the 7th. So I just replace every a with x and every b with 2. So x plus 2 to the 7th, that's going to be x to the 7th plus 7x to the 6th times 2 plus 21x to the 5th times 2 squared plus 35x to the 4th times 2 cubed plus 35x to the 3rd times 2 to the 4th, running out of room here, plus 21 x squared times 2 to the 5th plus 7x 2 to the 6th plus 2 to the 7th. And I'll have to use my calculator a little bit here. So 7 times 2 is 14. I'm going to get 21 times 4, so that's 84. I'm going to get 35 times 8, that's 280. Right, that was here, 35 times 8. I'm going to get 35 times 16. That's 560. Then next, I'm going to get 21 times 32. That's 672. 7 times 2 to the 6th, so 2 to the 6th is 64 times 7 is 448. And then 2 to the 7th is 128. So I can find that without doing all the work. Now, what I can do for this next one, example 5, I still picked a 7th power. I'm going to take the same result I have up here, this a plus b to the 7th, but now I'm just going to let a equal 2x, and I'm going to let b equal negative y. So, I had a to the 7th. So that's going to be 2x to the 7th. Plus 7a to the 6th b. 7a to the 6th b. Put the negative y has to go there. Plus 21a to the 5th b squared. Plus 21a to the 5th b squared. Plus 35a to the 4th b cubed. Plus 35a to the 4th b cubed. So that was 35a to, now 35a to the 3rd b to the 4th. 35a to the 3rd b to the 4th. Plus 21a squared b to the 5th. Plus 7a b the 6th plus b to the 7th. So 2 to the 7th is 128, x to the 7th, plus 7, 2 to the 6th, 64. We get x to the 6th, and we still have a negative y. Plus 21, we get 32 x to the 5th. Negative squared is positive, so that would be positive y squared. Plus 35, 2 to the 4th, we get 16x. Negative cubed would stay negative. Two to the 3rd power is 8. A negative to the 4th is positive. Then we get 21. 2 squared is 4. Negative y to the 5th stays negative. Then we get plus 7 times 2x is just 14x. And then negative y to the 6th goes positive. And then negative y to the 7th stays negative. So we get 128 x to the 7th minus 7 times 64 is 448. Here this is positive. 21 times 32, 672. 35 times 16, negative. So negative 560. I left off my x to the 4th there. Huh? Now 35 times 8. And that's going to be positive, so that's 280. 21 times 4, negative, so negative 84. X squared y to the 5th, plus 14x y to the 6th, minus y to the 7th. So we can get that whole result without going through everything else. Still a lot of work, but not as much as multiplying it out by hand. Sometimes we don't want a whole binomial expansion, we just want a particular term. And since there is a pattern to the terms, we can do that. The first term, notice, has a 0 in the bottom and b is to the 0 power. Second term has a 1 in the bottom and b is to the first power. Third term, both of those are 2. It's always 1 less, right? The r plus first term, I'm going to have r's in these places. So, how this works. The seventh term in a plus b to the 10th. So, seventh term means I'm going to have b to the 6th power, and I'm also going to have 10 choose 6. Right. So my n here is 10, and my r is going to be 6, because, again, up here, my r is what's in the bottom, and that always agrees with the exponent on b, which is always 1 less than the number of term. So the 7th term is going to be b to the 6th, so r has to be 6. I've got n is 10. So I'm going to have to figure out what 10 choose 6 is. So that's going to be 10 factorial over 6 factorial times 4 factorial. So 10 times 9 times 8 times 7 times 6, but then that's going to cancel out with all this stuff in the bottom, except for the 4 factorial. So this 6 factorial in the top cancels the 6 factorial in the bottom. I get 10 times 9 times 8 times 7. That gives me 5,040 in the top. I've got 24 in the bottom, 4 times 3 times 2 times 1. When I divide that, I get 210. So that's my coefficient. So 210, a to a power b to the 6th, but they have to add up to 10. So I have to say, what plus 6 is 10? It must be 4. So this would be the term that I would want. So here, fifth term in x minus 2i to the 9th. Again, I don't think of that. I just think of a plus b to the 9th. And I want the fifth term. So if I want the fifth term, that means I want b to the 4th. My n here is 9, so that means I'm going to need 9 choose 4. So I'm going to have 9 factorial over 4 factorial times 5 factorial. 9 times 8 times 7 times 6, times 5. That's going to start canceling out the bottom. 4 times 3 times 2 times 1. My 5 is going to cancel in the bottom. So 9 times 8 times 7 times 6 gives me 3,024 in the top. I divide by 24. That's 126. So this is going to be 126. It's going to be b to the 4th. And I say what plus 4 is 9. So it's going to have to be a to the 5th. But now I'm going to let a equal x, and I'm going to let b equal negative 2y. So I'm going to get 126 x to the 5th times negative 2y to the 4th. Negative 2 to the 4th is positive 16. So I get 126 times 16. That's going to be 2016 x to the 5th, y to the 4th.